Two equal and opposite charges separated by some distance is called an electric dipole. Di means two, so think of it as like two opposite poles of electricity. But my question has always been, what's so special about these dipoles? And for every dipole, there is something called a dipole moment. What exactly is that? And why is it a vector quantity? Why should we care about all these things? If you too have these questions, it's time we got answers for them. So let's begin. Our story begins with two charges, +5 and -3 coulombs, let's say. They're stuck. Let's imagine they're not allowed to move somehow. Then they're going to create electric fields everywhere, right? And the fields are going to interact and all of that. My question is, what would the field look like if we went very far away from this group? So let's say I'm zooming out, zooming out, zooming out, zooming out, zooming out. In fact, you know what? I zoom out so much that the two pretty much look like a single dot to me. And if you can't see it, that's the idea. It's so far, we've gone so far away. That's the theme over here, okay? The theme of this video is, what would the electric field look like if we go very, very far away? So let me show you that these charges are still there. You can imagine they're a millimeter apart, let's say, and I'm asking you the field, electric field, kilometers away. I want you to pause the video and think about it. Based on what you've studied so far, what would the electric field lines look like if we went very far away from this group? Okay, so I have a simulation and we will look at the simulation together. So right now we're looking at the field when we are close to these charges, +5 coulomb, -3 coulomb. Look at what the field line, how the field lines look like. The way I make sense of this is, let's imagine that each coulomb of charge, throws out 10 field lines. Then since this is 5 coulombs, it's throwing out 50 field lines. Now I don't know if there are 50 of them, but let's imagine 50 field lines are thrown out. Now this -3 coulombs of charge sucks in 30 field lines, and that's what's happening. Out of 50, 30 is being sucked in because it's negative charge. And so the remaining 20 are able to sort of like escape from this suction and eventually go towards infinity. And so when I go far away, it's these 20 that we'll be interested in. And I want you to look at it now. Look at these 20 which are going to escape. Look at how those field lines eventually transform into. Are you ready? Let's go. All right, here it goes. We're going farther away. Look at them. Look at them. They're becoming more and more straight. Can you see that? Look at what we see. We see that those 20 field lines are almost perfectly straight. They're perfectly radial. It looks like those field lines are coming from a point charge over here. Interesting, isn't it? So let's go back to our drawing board. And so what we saw is that when we are very close to these charges, the field lines are very complicated. But when we go far away, the 20 field lines which eventually escape become radial. And so from far away, because we're getting 20 field lines, it looks like it's coming from a single point charge of +2 coulombs. And that looks nice to me because when I take +5 and -3, keep them very close to each other, it looks like a single charge of +2 coulomb. That makes sense to me. Okay, let's play with this more. What if I change the charges? I make this +10 and -8, making sure the total charge still becomes +2. Now what would the field lines look like when I go far away? Would it still look the same, or do you think something changes? Can you pause and think? Okay, we can use the same logic as before. This time the +10 is gonna send out 100 field lines, but out of them 80 are gonna get sucked in. So only still 20 gets, 20 escape, and eventually they will become radial. This means from far away, it looks like nothing has changed. So what's incredible is that the individual charges don't matter. The strength of the group depends on the total charge, not the individual charges when I'm looking at it from far away. Let's play even more. The climax is coming, okay? What if now I increase the distance between them? It was 1 millimeter before. Now let's say I make it 2 millimeters. I double it. Or I make it 3 millimeters. I triple it. What do you think would happen to the field far away? When I go kilometers far away, do you think it'll matter? What do you think? Well, remember, these two dots are so close to each other that whether you bring them 2 millimeters or 3 millimeters or 5 or 10 millimeters, from when I look at it from kilometers far away, it's still gonna look like a single dot to me, right? So that's not gonna change anything when I look at far away. So as long as the distances are very small, the value of the distance really doesn't matter, which is also incredible. And finally, hopefully you'll agree, even the orientation won't matter, right? If I had kept that -8 on the left side or on the top or the bottom or somewhere over here, do you think it would have mattered? No, because the field is radial, right? So the whole thing will turn, but nothing changes. So if we summarize, we could now say, what does the electric field far away depend on? It only depends on, in fact, it's proportional to the total charge. That's all that matters. The individual charge, the distance between them, or their orientation, none of them matters. Only the total charge. And what's interesting is that there's nothing special about 2 charges. I could have had 3 charges or 4 charges. Oh, this means it's such a general result. This is a general result. If you give me any group of charges, it doesn't matter how many are there, if I want to look at the field far away, it only depends on the total charge. Nothing else. Beautiful, isn't it? But there are special groups of charges that completely break this. Any guesses which ones? Yup, the dipoles. Da da da. Now let's say instead of this -3 coulombs of charge, we had a -5 coulomb of charge. What do you think would the electric field look like when I go far away from this? Can you use this? Can you use whatever we learned so far about field lines and try to visualize this yourself first? So here's our simulation. What's different is this time all the 50 lines that are thrown out, all of them get sucked in. There is no escaping them. So all of them will loop back. So what will happen if I go far away? Well, let's look at it. Can you see? All the field lines are looping back. And so the field far away does not look radial. The field lines are no longer straight. We get something very different and of course, very beautiful. This is the dipole field. This is why dipoles are special. But my question is, what does the strength of the dipole field depend on? Because the total charge is 0. So what does it depend on? Well, let's do the same exercise as before. First, let's change the individual charges. Instead of +5 and -5, what if I make them +10 and -10? Can you visualize what the new field would look like? Would it be the same? The pattern would be the same, but would the whole thing look the same or would it change? Well, if I make it +10 and -10, this time 100 field lines are coming out and all the 100 field lines are looping back, which means there'll be twice the number of field lines compared to before. So this means the electric field will double everywhere. Individual charges matter. Let's look at that. Here it is. This is what happens when I double them. The beauty is the total charge is still 0. But the individual charges matter. They are doubled, and so the field everywhere doubles. So let's write that down. So this time I find that the electric field far away, due to dipole, it does not depend on the total charge, because total charge will always be 0, but it depends on the individual charge. And let me just draw the field lines. All the field lines get sucked back in. And so this is what we saw. Okay, second question. What if I were to increase the distance from 1 millimeter, I make it 2 millimeters or 3 millimeters? Just like before, when I look at it from far away, it looks like nothing has changed. They will still look like a dot to me. But do you think the field lines would change? Your mind is gonna get blown now. Let me show you the simulation. Here's the simulation. And I've zoomed in so you can see the charges going farther and coming closer. All right, so let's see. Look at the field lines far away. See what happens as I move them. All right, what do you see? You find that when I move the charges farther away, the field lines actually come closer over here, which means the field gets stronger. If you think about it, that's mind-blowing. If I make that distance from 1 millimeter to 2 millimeters, when I go kilometers far away, it still looks like a dot, but the electric field over there has doubled. That's just, I don't know, it's hard for me to comprehend. Why is that happening? Well, that's because when the charges are closer, if you bring them closer, then the field lines get sucked very quickly, and therefore the field lines go far away very quickly, and so the field becomes weaker everywhere. So the mind-blowing thing about dipoles is that the field far away depends on that teeny tiny distance between the charges. In fact, it turns out to be proportional to it. But here's my question. What if I were to double the charges and bring them closer and make the distance half? Now what would happen to the field far away? Well, now you will see if since this got doubled and this got half, the effect cancels out and the field far away stays the same. Ooh, that means what does the field far away due to a dipole depend on? It doesn't just depend on the charge. It just doesn't depend upon the distance. It depends on the product. The product now decides the strength of the dipole. And therefore, we give a name to this product. This product is called the dipole moment. Dipole moment. The symbol for that is P, and the dipole moment is the product of the charge on the dipole and the distance between the two charges. And why should we care about that? Because that represents how strong the dipole is. And so tomorrow, if you have a dipole and you want to know what's the effect of it somewhere far away, you don't need the individual charge, you don't need the distance, you don't care about them. All you ask for is the dipole moment. All you need is the product that decides the strength of the dipole. Finally, what if I change the orientation of my dipole? For example, I bring that -5 coulomb up. Would the field everywhere stay the same? Well, now, because the field is highly directional, the whole field is going to change. And so, again, what you find is that if you make a tiny change in this very tiny thing, you change it, field kilometers away, everywhere is going to change. This time, orientation matters. So if you just tell me the value of dipole moment, I can't tell what the field looks like everywhere. You have to tell me the orientation as well. And that's why, to take care of the orientation, we make dipole moment a vector quantity. So our dipole has a direction. So how do we choose the direction of the dipole though? Well, look at the field. Well, over here below, you can see the field is being blown downwards, and from here the field is being sucked. And so we like to say the dipole has a direction that looks like this. And if you think about it, this was the negative charge. The blue is a negative charge. This is the positive charge. And therefore, the direction of the dipole moment is from negative to positive. From -q to +q. That's the direction of the dipole moment. So long story short, why are dipoles special? Well, because when you are far away from any group of charges, which are not dipoles, the field that they create does not depend upon internal details. Because it looks like a dot. The only thing matters is what's the total charge. But when you're dealing with a dipole, when you go far away, even they look like a dot, but the field they create depends on all the internal details. And guess what? Dipoles are found everywhere in nature. A lot of molecules like water, for example, are dipoles. And so knowing their strength or dipole moments help us understand how they interact with other molecules and eventually help us understand how these elements or compounds behave.